Then your switching leg can be implemented with like this. For example, you can use the MOS FET or you can use IGBT. Then there are many kinds of switching devices, but they are common recently. So usually for automotive power conversion systems, you use IGBT, but recently the silicon carbide MOS FET is also actively applied in automotive applications because their excellent switching characteristics. Then 미안해. 이렇게 인기가 많아요. 전화가 막 연속으로 오네. So, let's consider the anti-parallel diode, 역병렬 diode. We call anti-parallel diode. Then why do you need to have the anti-parallel diode? For example, most of your loads are inductive load. Probably almost over 90% of your load is inductive load. Then, inductive load create reactive power. Reactive power means you see opposite way of current path. Then, even if your switching device is opposite is turns on, when you have the inductive load, your current could flow in opposite way, like that. In MOS FET, basically, as long as you turn on the switch, then the current could pass through the channel in MOS FET. But in this IGBT, there's no capability to reverse current. Then you should equip the diode. That is the anti-parallel diode. Then if you don't have anti-parallel diode, then your device will be also failed. And as I told you, the performance of anti-parallel diode is very, very critical to increase the performance of your entire power conversion systems. For example, you know that there are several types of diode. The general purpose diode and fast recovery diode and ultra fast recovery diode, and also you know the Schottky diode. Among them, which one is the fastest one? Schottky, right? The Schottky is the fastest one. So you usually like to equip the Schottky diode in power conversion systems, but the problem of them is that the lower the voltage rating. That's why we have the silicon carbide Schottky diode. Although that is very expensive, the power conversion systems basically like to equip the silicon carbide Schottky diode. Then normal applications, if your application doesn't require very, very high performance, then usually we use fast recovery or ultra fast recovery. If you want to implement very high power conversion systems, actually it's very difficult to purchase the Schottky diode. There's no selections. Then you need to go with the ultra fast recovery diode. Okay? If you want to use the general purpose diode in your power conversion system, then you shouldn't put them in here. The general purpose diode can only suitable for the 60 hertz or very low frequency. The fundamental component. To rectify the low frequency fundamental frequency, then general purpose diode is okay. But the high frequency operation, if you have the GP diode, then your power stage will see a lot of heat. Then finally your switch will be failed. Then, okay, let's see this circuit here. What is this circuit? What's the name of this circuit? You have 60 hertz here. Yes, full bridge rectifier. The operating frequency of this full bridge rectifier is just a 60 hertz. This is a low frequency, right? Then, for this diode, you have, for example, general purpose diode and Schottky. Which one is stable here? General purpose. Why? Can you apply Schottky here? Or fast recovery diode here? You can use it. But the problem is that, we know that diode has forward voltage drop, right? Usually, your switching frequency, your operating frequency is fast. Your VF is also increased. So, under the same ratings, the VF of GP is the lowest low, and Schottky is high, and FR is within the GP and Schottky. So, in this case, VF is critical. So, you should use general purpose diode here. If you use the Schottky, still your circuit can work, but the entire efficiency could be dropped because of high VF. Then what about the price? This is the cheapest. This one is what? Expensive. This is what? Between GP and Schottky. Okay. There are some kinds of active rectifiers. For example, this. And let's just skip because you didn't learn about this. So I will explain it later. Okay, so now let's simply evaluate this circuit. You guys did the analysis of this circuit several times, but I will just do again here. If your Q1 is turned on, Q2 is turned off, your VAN, this is what defined as pole voltage, is VDC over 2, right? If your Q1 is turns up, Q2 turns on, VAN is what? Minus VDC over 2. And when your both switches turns off, then VAN can be either VDC over 2 or minus VDC over 2 according to the direction of your current, right? Then 1, we don't use this case, right? So as I told you, this is critical. Okay, then let's simply talk about the switching function. And your output voltage can be actually expressed as the switching function, the combinations of switching function. Okay, let's simply define your Q2 as like this. Because your Q2 operates complementarily, then Q2 equals what? Bar Q1. Then this is simply written as 1 minus Q1, right? So if your Q1 is 1, Q2 is 0. Your Q1 is 0, your Q2 is 1. And with this switching function, you cannot implement 0, 0 or 1, 1, but we just assume some ideal case. Then we can define switch function as like that. And let's define your SHB. HB stands for half bridge. Your HB is 1 over 2 and Q1 minus Q2. This is just a simple definition here. Then your VAN. This is what? Pole voltage, right? the pole voltage can be written as like this. Here, Q1 multiply VDC over 2 plus Q2 multiply minus VDC over 2. Then your Q1 is 1. You have VDC over 2. And in that case, your Q2 is 0 here. Then you don't see this voltage. Then this can be, in fact, written as like this, as HB times BDC, like this. Then, in fact, you can also define your switching function as like this here. Then, what does it mean? If your S is 1, your VDC, your VAN is VDC over 2. Your S is 0. VAN is VDC over 2 with minus sign, right? It means you can define the switching function in different ways. There are many expressions. Then let's define the switch current with the switching function. The switch current, what is the switch current? The current passed through the switch here. So IS1 is current passed through the Q1. IS2 is current passed through the Q2. Then here, your IS1 can be written as Q1 multiply IO. IO is your load current, right? So when your switch is Q1 is turns on, then IS1 is identical to IO, right? When your Q2 turns on, IS2 is the magnitude of IS2 is same with IO, but the polarity is different, right? That's why IS2 is written as Q2 multiply minus IO, right? Now you understand IS1 and IS2 with the switching function. Then in fact, your IS1 and IS2 can be also expressed as like this, using the equations this and this, right? So if you put the Q2 equal 1 minus Q1 here, then after that you can do some manipulation, and you can obtain IS1 as like this. Once you obtain IS1 as like this, then you can simply obtain IS2 like this. Yeah. This is just a simple manipulation of equations. Not very complicated. Okay, let's define the carrier and some PWM indexes like that. Okay. Basically, the power electronic circuit usually employ the PWM. PWM stands for pulse width modulation. To create the PWM, you should have basically two waveforms. The first one is apparently your reference. Reference is necessary. And the second one is what? The carrier. So, the PWM can be implemented with like this. You have the reference, you have carrier, right? So, here we employ a triangular shaped carrier like this. Then, if your reference is like this, then the output of this is, for example, S. Output of this op-amp comparator is what? Like this. And if your reference is reduced to this like this, then your output will be like this, right? Then by doing this implementation, then you can adjust the duty ratio. So here you can define some terms. The peak of the carrier is AC here. The peak of your reference is AR. Then we can define amplitude modulation index, which is written as MA. MA is what? AR over AC. Also, we can call simply modulation index, 변조지수. Or we can call them as voltage modulation index, 전압 변조지수 in Korean. This is a very, very important definition in inverter applications. Then the frequency modulation index, MF, is defined as FC over FR. FC is the frequency of your carrier. FR is the frequency of your reference. This is also important when you want to drive very high-speed motor. For example, very high-speed compressor or even electric vehicle. The recent trend of electric vehicle motor is what? High speed. Because when your motor is high speed, then you can reduce the entire size. So this is also important, but this is the more important. Okay, and this figure shows that the switching frequency and the current ripple here. Here, this is your carrier and reference, and this is your modulated waveform. In this case, your reference is, for example, 10 Hertz, and your switching frequency, this is the carrier frequency is 100 Hertz. And in this case, your reference is still 10 Hertz, and your switching frequency is 10 kHz. And apparently, the current ripple wise, this one is much, much smaller than this. It looks like almost the fundamental components. So the high frequency is, well, it is good. Achieving high frequency is good. But there are some limitations because if you increase your switching frequency, then you also increase the switching loss. All switching devices has two types of loss. First one is conduction. Second one is switching loss. Conduction loss is what induced when your current passes through your switch. And switching loss is induced by on and off operation of your switches. So if your switching frequency is high, then switching loss also increased. Okay? So apparently high frequency is important because to shape your current clearly, but it also create the switching loss. Also, consider your magnetic component, like the inductor. Inductor also has what? You know that this curve and this region, the frequency of this movement is also very high. Then also it create additional loss. So implement of high frequency is very important to make the compact power conversion system, but it has also limitations according to the switching loss. Okay. Then you can also define some terms here. This is what? The linear modulation. Linear modulation. And another term here is what? Over modulation. In linear modulation range, if you increase your voltage reference, then your modulated waveform is also linearly increased. But in overmodulation region, as you can see here, your carrier, your reference is larger than your carrier, right? Its maximum is what just looks like this, right? So you cannot actually implement this part, okay? So in this case, your output voltage is what? Distorted, not sinusoidal. So in linear operational range, your output current is like this, sinusoidal, but in overmodulation region, your output voltage is non-linear. So your current is distorted as like this, right? So simply think about this. If your current is distorted, then it creates the torque ripple, okay, in the electric motor system. And it also creates what? The reactive power in the power electronic system under the utility applications, okay? But especially in motor drive applications, you frequently see the overmodulation region in motor drive application because your battery, actually this is very closely related with the DC link voltage, right? Because this is the peak of the DC link voltage. So in motor drive applications, you don't have enough room for your DC link voltage, then you frequently see the overmodulation operation. Okay? Okay, let's implement the half-bridge inverter and open your PSIM and implement your circuit as like this here. Then here, your simulation control, your time step is what? 1 microsecond. And you simulate for 0.1 second. Okay. And you have half-bridge inverter like this. Here you have the VDC, 100 volt and also 100 volt, and you have ground here. And I just employed IGBT switches. And to drive your switch, you should have the switch controller here. This one is the switch controller. And 1 millihenry of inductor and 2.5 ohms as a load. And see this. Your voltage reference here, this is sinusoidal waveform, and its peak amplitude is 50 multiplied square root 2. What does it mean? Its magnitude is RMS 50 volt, right? And frequency is 60 hertz. 60 hertz. And what about your carrier? Carrier is simply set as like this. Since you have entirely 200 volt, right? So peak to peak is 200. But this is a half-bridge inverter. Your ground is here. So you should have DC offset minus 100 volt, right? Then you can create 100 volt and minus 100 volt carrier here. And frequency. Carrier frequency is 1 kilohertz. So here, if your current is like that, then this is okay, right? Then, now, let's change your carrier frequency. Originally, it was 1 kilohertz. Now, you change it to 10 kilohertz. Then compare the result of the current, okay? And also, think about it. Here, I told you your reference voltage peak is 50 multiply square root 2, right? Then its RMS value is what? 50 volt. Then what is your resistance of your load? Your resistance is what? 2.5, right? Then what would be the RMS current passed through your resistor in your inverter? What is the value? Current in RMS? 50 over 2.5 is 20, right? Then your RMS current is 20 ampere, right? Then 50 multiplied 20 is what? 1 kilowatt. So in this case, you transfer your power from DC to the AC with 1 kilowatt, right? Then what about the power factor in that case? Is it unity? No. Why? Because you have the inductor. Apparently, in this case, your power factor would be lagged. It is not 1, less than 1, okay? Then check that. Okay, this is my simulation result, and it is much what the clear compared to the previous case. You can also change your inductance. If you increase your inductance, you can additionally reduce the current ripple. But in that case, which one is different? Your power factor is also different. But your transferred power from the source to, the active power is the same, right? Because your resistance is the same, right? Look at this. Then, if you check the element, other, and probe, and you can see the many meters. Here we have wattmeter, three-phase wattmeter, and bar meter, and BA. This is the apparent power, 피상전력. Then let's see wattmeter here. Then bring wattmeter and insert the wattmeter in here. Okay. Then in wattmeter you have two terminals. First one is just watt. The second one is watt hour. That is what? Energy, and that is the power. And we can see the power here and energy here. Then P and E. Then the simulate again, and your output power is like this, and your energy is what? Like this. Can you see here? Okay, let's simply change the total time to 1 second. Then here, your output power is close to 1 kilowatt, right? This is what I expected, right? And your energy is increased because you continuously continuously supply the energy from DC to the AC, okay? 그렇죠? 이거 이해합니까? 네. 자, 넘어가겠습니다. 실습은 충분히 했을 거라고 보고. 하나만 더 해볼까? 지금 50 곱하기 루트 2잖아. 그거 100 곱하기 루트 2로 한번 바꿔봐. 그러면 여러분 이제 과변조 모드로 넘어갈 거야, 그게. 전류 모양이 어떤지 한번 봐봐. 거의 화면을 꺼 할 때마다? 안 꺼도 되는데? 어? 상관없어. 전류 모양 한번 보세요. 확대해서. 네, 전류 모양이 어떻습니까? 찌그러지죠? 네, 찌그러집니다. 여기 과변조 모드로 들어갔을 때야. 자, 이제 여기 단상 풀브리지 인버터 봅시다. 단상 풀브리지 인버터 봅시다. 자, let's see here. This is the structure of a single phase full bridge inverter. And you have the single VDC source. But to explain this circuit simply, I just assume that there are two different sources as like that. And here, we just have the point N. That is a neutral point. But in real application, you shouldn't have this, right? Okay. You have the Q1, Q2 switching leg, and you have Q3, Q4 switching leg. So basically, single-phase full-bridge inverter has two half-bridge inverters. It means you have two pole voltages, BAN and VBN here. So according to the switching, the combinations of switches, then you have the pole voltages as like this here. Here, your Q1 is 1, Q2 is 0. Then your VAN is what? VDC over 2, right? And your Q3 is 1, Q4 is 0. Then your VBN is what also? VDC over 2. Since your output voltage VAB can be written as like this, VAN minus VBN, right? Then 0.5 VDC minus 0.5 VDC is what? 0. So zero voltage is applied to your load. And in this case, Q1 is 0, Q2 is 1, then your output voltage VAN is minus 0.5 VDC. And Q3, Q4, this is 0 and 1, your VBN is also as like this. Then your output voltage is still 0, right? Now what about this case? Q1 is 1, Q2 is 0, so your VAN is 0.5 VDC. Q3 is 0, Q4 is 1, your VBN is minus 0.5 VDC. Your VAB is what? 0.5 VDC minus 0.5 VDC, then that is VDC, right? Now what about this case? Q1 is 0, Q2 is 1, your VAN is minus 0.5 VDC. Q3 is 1, Q4 is 0, and your VBN is 0.5 VDC. So, if you calculate VAB, that is minus VDC in this case. So, previously, in half-bridge inverter, your output voltage has only two. First one is VDC over 2 and minus VDC over 2. But in this case, you have VDC, minus VDC, and 0 voltage. So, it is 2 level or 3 level? 3 level, right? So, the single-phase full-bridge inverter has a capability of the 3 level inverter, basically. And your output voltage, previously, your entire input voltage was what? VDC. And your output voltage was, maximum is VDC over 2. But in this case, your input voltage is the same to VDC, but your output voltage maximum value is VDC. So, DC link utilization is what? Twice than the half-bridge inverter. Okay? Then, let's see this inverter. This is the 3-phase inverter, and the 6th step, it is basically depends on the modulation strategy. But if you just, you can just simply ignore here, and this is the structure of the three-phase inverter. Three-phase inverter has what, three half-bridge inverters, and we need to define some voltages. The first one is VAN, VBN, VCN. That is pole voltages, right? And we can define phase voltage. Phase voltage is defined as this point and what, S. That is the neutral point of your load. So if you consider the three-phase motor, that is what, the neutral point. Then VAS, VBS, and VCS are defined as phase voltage. And line-to-line voltage is the voltage between two switching poles, VAB, VBC, VCA. That is the line-to-line voltage. Then, in the viewpoint of your load, which one is important among three voltages? In your viewpoint, which one is important? Phase voltage, right? So, phase and line-to-line voltage is important. The pole voltage is not very important to your load side. Okay. So, think about this. In this configuration, your pole voltages can have what? VDC or minus VDC. I mean the VDC over 2 or minus VDC over 2. This is the same to the switching the value of the half-bridge inverter. And what about the line-to-line voltage? Assume that in this case your VA, this is connected to here, VB connected to here. The voltage is what? VDC. Okay? If you look at VCA, then voltage is what? Minus VDC, right? And what about VB and VC? That is 0 volt, right? So, in terms of line-to-line voltage, you may have three voltages: VDC, minus VDC, and 0 volt. And what about phase voltage? What about phase voltage? Phase voltage, I can draw the equivalent circuit of this structure. Point A. Point A. Point S. Right? Then point B, point C. Okay? Point B and C, right? Then if you have the same impedance, right? So, in this case, your VAS is what? AS is 2 VDC over 3, right? What about VBS and VCS? The magnitude is VDC over 3, but your polarity is opposite, right? So, for phase voltage, you may have 2 VDC over 3 and VDC over 3, minus VDC over 3, and minus 2 VDC over 3. You may have these voltages. So, this is the pole voltage of three-phase inverter here. Then your VAN, VBN, VCN may have plus minus VDC over 2 like this. And its phase are different. VAN is what? The phase 0. VBN is what? This is leg to the VAN by what? 2 pi over 3, 120 degree. And VC is also like this. That is what? Switching pole voltage. And what about this? This is your line to line voltage. You have 3 voltages. And this is your what? The phase voltage. Phase voltage. As I told you, you have 1, 2, 3, 4. 1, 2, 3, 4 voltage levels. Okay. So this table shows the switching status and pole voltage and phase voltage. Okay, then you can simply refer the table. And let's see the voltage expression using the switching function here. Okay, let's see here. VAN, this is the pole voltage, right? And this can be also written as like the VAS plus VSN. What does it mean? VAN is what? VAS plus VSN. Does it make sense? Okay. Then VBN is also VBS plus VSN, right? VCN is also like this. So your pole voltage can be written with phase voltage plus what? VSN. So VSN here is called it the common voltage or neutral voltage. Sometimes we use the term offset voltage. Common voltage, neutral voltage, offset voltage is basically the same here. Then, let's see here. If you sum these pole voltages, VAN plus VBN plus VCN is what? VAS plus VBS plus VCS plus what? 3 VSN. Okay? By the way, that is the phase voltage. And you don't have neutral point, right? A neutral line. You don't have neutral line in this case. Then the sum of phase voltages are what? 0, right? And if you apply this condition, then this term is removed. Then you only have 3 VSN. So finally, your common voltage VSN can be written as 1 over 3 multiply the sum of the pole voltages. And in half-bridge inverter, I introduced these switch functions, right? Then if you put these switch functions here, then the equation can be simply derived as like this. So VSN can be VDC over 3 SA plus SP plus SC minus 3 over 2. So now you know VSN here. So if you put this relation here, then your VAS, VBS, and VCS can be simply summarized as like this. So this VSN is pretty important. Physically, it creates an EMI source, and it also creates the leakage current in three-phase inverter. How? Because, okay, this is a simple circuit, but all the circuits, where is the ground here? Your ground can be here, but you may have the real ground. Then there's leakage capacitance, the plastic capacitance. And through the plastic capacitance, you see the leakage current, and this can be the voltage source of the leakage current. 잘 알겠죠? 자, 썸하면 극전압이에요, 극전압. 얘는 상전압이야. 얘는 옵셋 전압이야. 근데 이 옵셋 전압이라는 놈 혹은 공통 전압이라는 놈이 극전압을 3으로 나눈 거야. 그렇죠? 그럼 얘는 어딘가 이 전압이 있으니까 뭔가 얘가 전류를 만들어내겠네. 그 전류 어떻게 만들어내? 여기 이제 리퀴지 성분들이 있다는 거지. 플라스틱 성분들이 개통해서 우리가 전류를, 누설 전류들을 흘릴 수 있다. 이거를 이용을 해서 우리가 이 3장 인버터 같은 경우에는 여러 가지 전압 변조 기법들을 적용을 합니다. 예를 들어서 우리는 사인 웨이폼을 부하에다 인가하고 싶죠. 사인파를. 근데 실제 극전압을 사인파로 안 주는 경우도 있어요. 극전압을 사인파로 주지 않지만 실제 부하에는 사인파가 인가가 돼. 그런 경우들이 왕왕이 아니라 삼성 모터 구동 시스템은 거의 95% 이상 다 그렇게 합니다. 다 그 이유가 있어요. 그 이유는 우리가 차차 배울 건데. 그래서 이걸 이용을 해가지고 우리가 그렇게 구동을 할 수 있겠다. 자, 그래서 다음 시간에는 이 3상 인버터 조금 더 우리가 테스트를 좀 더 해보고요. 그리고 시뮬레이션을 좀 하고요. 그리고 여러분 교재는 제가 이제 일단 이쪽 좀 끝난 다음에 교재에 있는 내용은 또 다시 또 진행을 하도록 하겠습니다. 네. 질문이 없으면 오늘 이만 마치겠습니다. 수고했어요.